All right, good evening, everybody. Welcome back. To see something to be back as well. And well, I'm in front. So welcome to the July meeting, so it's very good to see so many of you here. It's given us a bit of feedback so that you're ready, I think. I know I am. So tonight we'll be having a talk from Jim Dunlop here from the ROE. So exploring the cosmic norm with James Webb Space Telescope. It's a new picture coming out next week. Is there something?
Week and Tuesday is the date of the week.
Tuesday, yeah.
This is a very
topical field, is it?
I don't know actually. Yeah. You'd think it was a military secret, so we'll find out.
It's all over the internet. Just a housekeeping to get to sort of start off with. To say welcome everybody, also members and visitors. And we've got a few visitors tonight. Rosa, put your hand up so we know who you are. Zach. Ian Taylor, welcome back. Joe. Joe, is it Joe? Joe and Charlie. Yeah, welcome. So everyone, be nice, we're all nice people, and then when we get them joined, we can then just go back to being normal. Okay, look at first aid, usual housekeeping. Do we have any first aiders in? One first aider, two first aiders, so that's perfect. So if any of you feel a bit poorly, go. I am, but don't come to me. Fire. If you have a fire and got to leave in a hurry, you'll see a blur shaped me going out that door. Just follow me. If the fire is there, you go out. There's an emergency exit right in the corridor here. If you're in the canteen, there's one at the far end. Obviously, the main entrance as well. We'll muster in the car park. Now, the tick list in this tells us how many people are here. So if you have to leave at half time, please take the name off the tick list. So we're not sending firemen, fire people, can't say firemen anymore. Into here, looking into a burning building, looking for you when you're down the road and having a beer. Okay? So if you can let us know if you're leaving at half time, right from that. I don't know why it would. Second half time, you're really good at telling me. Mobile phones, remember to turn them back on when you leave. Reverse that, and you can turn them off now or turn them on to silent, please. I forgot to do one last month, but I don't know. Okay, meet and brief. For those of you who haven't been to Signal before, so we'll have the main talk by Jim tonight. Then we'll have a tea and coffee break. After that, Stuart can't be with us tonight. He's had to take his wife into hospital, so he can't be here tonight. But very, very short notice, about 24 hours ago, I think it was. I phoned Tim and said, "Tim, you've got an Astro Basics up the sleeve you could do for tonight." And he went, "Yeah, no problem." Or what's that effect? And so that's in the second half. So now I'm just going to talk a little bit of club news. Just before I start though, I want to know some of you do leave at half time. Just say about how we're trying to go forward with the meetings. What we've decided is during the summer we're going to try and do meetings like this. And then in the winter months we'll do a few on Zoom. Because sometimes we have issues with, especially if you've got speakers coming up and down south or anything with weather and traffic, because the results we had back from that survey I sent out to you was you want some sort of Zoom meetings as well as physical meetings. Okay. But to try and make up for the loss of the physical meetings we had in the winter, we'll be doing, what we call morning astro meets. Basically, we just spur of the moment, right? The sky's clear, we're meeting here tonight. We just all go somewhere, like we did on Sunday. A few of us went out to the park at the solar telescope. And a few members of the public came along and I looked at the sun. Some will be for members, some will be public ones as well. Okay, so we're going to try and with a bit of a balance going on so we can try and keep everybody happy. I know how difficult that can be. Right, so on to the main speaker tonight. A little bit about Jim. Now, I used to do a Google search, you remember years back. 2.5 years back, maybe. They seemed to go terribly wrong when I'd done one search and came up with a prisoner in some jail in Australia. So I thought, so I can't. So I now asked the speaker to give me a little bit of a bio of themselves. It's a lot safer.
You've got that.
I can't remember who it was. So Jim was born and raised on the Clyde. Clyde Coast in Scotland. He studied physics at Dundee before moving to Edinburgh, where he obtained his PhD in astrophysics in 1988. Someone forgot to turn the phone. We all look at you when your phone goes. After 7 years working in England, where he helped establish the astrophysics group in Liverpool, he returned to the University of Edinburgh and he worked at the School of Physics and Astronomy. And he's worked there ever since, apart from the two periods in Vancouver. In 2004 to 2008, he again, and again from 2015 to 2018, he was the head of the University Institute for Astronomy. Since 2019, Jim has been head of the School of Physics and Astronomy at Edinburgh University still.
For my sins.
For your sins. Just really enjoying it. When you read the bit of this, you see why you enjoy it. Jim is an observational cosmologist. He uses the world's biggest telescopes, including telescopes in space such as the Hubble Space Telescope, Vista, and ALMA in Chile, ALMA telescope in Chile, to study cosmic history back to the formation and birth of stars and galaxies. Jim's research has made an extensive use of NASA's facilities, especially the great observatories just mentioned, and often pushes these space telescope platforms to the limit of their capabilities. He was the first non-US PI. And when I say PI, private investigator, surely not.
Principal is this.
Principal, I've got to look it up. I thought, yeah, I thought, surely they knew, microscope at the time, magnifying glass, not a big telescope. PI of a major 300-hour legacy observing program on the Spitzer Space Telescope. Was European lead on 1,000 orbit. So you kept Hubble point in the same place for 1,000 orbits or something, I'm thinking.
2 or 3 places.
2 or 3 places. HST Treasury program. And he co-led the HST Hubble Ultra Deep Field in 2012. Now we've all seen the Ultra Deep Field image, haven't we? So this man had more to do with public. Still, I still look at that picture now and think, wow. So Jim is now the PI of the largest approved Cycle 1 James Webb Space Telescope. Galaxy program, Premier, here we go. Public release imaging and extra galaxy research. Due to commence observations in July.
With the James Webb Space Telescope. This is the other thing. If you take a space telescope and you want to see a long way, you have to take a long integration. So you have to look at the same place for hours and hours. So when I talk about the survey, that's one of the fields we're going to do. And we're only going to do about 10% of each. So these are tiny kind of pencil beam needles into deep time, just hoping that that bit of the universe that you got to is typical. Because you can never survey the whole sky to the depths to look back to the beginning. So I've said here, we're lucky we live in a thin disk. If humankind had lived in an elliptical galaxy, we probably would have never done cosmology, because we would have seen out of it in the direction. So there's a kind of historical good fortune that we live in a thin disk and we can look out at the galaxy a long way. So that's my geography lesson. Now, again, we'll think about things, but this time we're looking back in time. So whenever you look out and see another object, it goes light when we get a finite speed, as I guess first predicted by James Clerk Maxwell and then adopted by Einstein. We know the speed of light, and so when you look out, a finite step in distance is a step back in time. And so cosmologists talk about look back time. When you look at an object, how far back in time are you looking? When you look at a far away object, how much further back in time are you looking? It's an important concept, because some people think, you see these deep fields with tiny little galaxies, go, oh, they're very far away. I don't care if it's far away. We're only looking at it far away because we want to look a long way back in time. Otherwise, it wouldn't be worth the effort to just study some nearby galaxies. It would be a lot easier. Some context helps with this. So here's the Hubble Space Telescope. And this is an interesting comparison with the James Webb Space Telescope. The Hubble Space Telescope, as you can see, is not very far away from the Earth. Okay, that's a real photo. In fact, it's only about 350 miles above the Earth. So its orbit, what's 350 miles away? Is London about 350 miles away? Something like that. So it's really very low down. This is both bad and good. It's bad because in a low Earth orbit like this, it goes around every 90 minutes. So if I want to look at a galaxy over there, I can only do it for about 40 minutes and then I'm around the other side of the Earth. So scheduling the Hubble Space Telescope has always been a nightmare because this thing goes round and round every hour and a half. And you go, oh, look over there, or no, look over there, and schedule somebody else's observations over there. It's good because the Hubble Space Telescope is the worst telescope ever made in the history of telescopes until the shuttle astronauts went and fixed it. Okay, and if I hadn't been so close, they couldn't have gone and fixed it. And they were lucky because they found the same laser setup that etched the mirror still there in the perpendicular lab and realized that the laser beam, which was meant to bounce off a mirror, was missing the mirror and hitting the metal ring around the side. So they actually were able to reconstruct exactly what was wrong with the telescope, build a bunch of other optics, fly up and stick this thing in front of the mirror and fix it. So Hubble Space Telescope got off to a famously disastrous start, and then in classic NASA style produced heroic astronauts who fixed everything. So it was a win-win in the end for NASA, but it didn't start with. Just as well, James Webb Space Telescope, from what we're hearing and seeing, looks like it works because no astronaut could go to the James Webb Space Telescope and fix it. 350 miles, turns out the light travel time is only 0.02 of a second. So when you look up at the Hubble Space Telescope, and you can still do so, you're seeing it as it was only 2 milliseconds ago. So who cares? You look at the moon, 1.3 seconds ago. So if the moon disappeared, which is very unlikely, you wouldn't know for 1.3 seconds. The sun, which we know is about 93 million miles away, so I'm kind of mixing and matching imperial units, so it's nothing political going on here. You see the sun as it was 8 minutes ago. So part of this, it's interesting that you're looking back in time, but this is unexciting amounts of time, right? Because light is so quick. Look out the other direction, depending on where it is in its orbit, you see Jupiter about half an hour to an hour ago. There's a real picture of Pluto finally taken in 2015 by the New Horizons spacecraft. Pluto, the light from Pluto, which you can, I mean, it's still an argument whether Pluto's a planet or not, don't really care. It's really a rather round looking rock, which we call a planet. It takes 5 hours for light to get from Pluto to us. It took the spacecraft 10 years to get there because nobody yet has invented anything close to the speed of light for a spacecraft. But if you look at the nearest galaxy, the Andromeda Nebula, F31, which you can see with the naked eye, a nice dark night, particularly if you look slightly to the side. Suddenly, I mean, I already said how close the next star is in my scale model, beach ball to Australia. So when you get to another galaxy of another 100 billion stars, the closest galaxy you're seeing it as it was 2.5 million years ago. Now, I know there's been a new fossil discovered this week. That's kind of the age of humans, I suppose. So if you sent a message to Andromeda and they said, bugger off or something, it'd be 5 million years before you got the answers. So it would be a very good conversation. Okay, but this is just the nearest galaxy. This is where things get a bit crazy. The Milky Way and Andromeda are in a group of galaxies, some smaller dwarf galaxies. So the communication in the local group takes 3 million years. Here's a nice Hubble picture of a cluster of galaxies as it was about 5 billion years ago. So now you're talking serious time. A lot of the stars in that image won't exist anymore. They'll have died out in the 5 billion years since the light is taken to get here. And here's the Hubble ultra deep field we talked about. There was an optical image taken by Hubble in 2004, and then the one that Pete mentioned that we did following it up with the infrared camera was in 2009, and then 2012 again. So this is a tiny, tiny patch of sky where they looked at the same patch of sky for hundreds of hours with the Hubble Space Telescope. And that's, at the moment, waiting for James Webb, basically one of the most distant images ever taken. And the faintest galaxies in this image, you're seeing them as about 12.5 billion years. Now, interestingly, it turns out that we now know the age of the universe very well. We're actually seeing 90% of the age of the universe back to the faintest galaxies and stars. So we already know there were things, stars and galaxies, 90% of the age of the universe ago, which people didn't used to realize it. So we're seeing a lot of the way back. Can we see any further back? Well, let's hope this little video works. I'll try. This will be my only equation, I promise. So it's almost impossible to get me to talking about something called redshift. And this is easy to understand. I mean, some people talk about it as a Doppler shift or whatever. This little letter Z is a symbol that somebody invented for redshift. It's also a stupid symbol for the word redshift, but it's a symbol they decided. And the redshift really quantifies how fast an object is moving away from us as the universe expands. And it turns out that the faster something's going away from us, the further away it is as well, therefore the further we're looking back in time. And the simple way to think about redshift is that it's, imagine the light leaves this galaxy a long time ago and it's traveling across the whole universe, it's expanding. As it travels, the light expands as well. So what maybe started off as an optical bit of light gets stretched into the infrared by the time it arrives here. And so 1 plus the redshift is the observed wavelength of light divided by the emitted wavelength. So if redshift is 0, Z of 0 then the wavelength observed is the same as the mathematical. And it turns out everything expands together. So 1 plus Z is the size of the universe now over the size of the universe then. So if I see a galaxy and we can measure its redshift from the spectral light at redshift 1, then that means the light was emitted in the universe was half of its present size. If it's redshift 2, at 1, get 3, the light was emitted in the universe was a third of its present size. And so when you're looking back at the time when the universe was much smaller, you're also looking back in time. So here is this is a spectrum of light. So this is the light from a galaxy split up by wavelength. And this is a theoretical spectrum. And when you use these big telescopes, and most of you in the room will know that you're doing kind of crude spectroscopy through filters of different colors. So through this filter, you get all the blue light, through this one, the green light, then some red light. Then there is the infrared filters that you can't see with the naked eye, but you can with these telescopes. And what happens as the galaxy gets redshifted is that it gets stretched away to high redshift. So at the time you're at redshift 10, when the universe was an 11th of its current size, 1 plus Z. The light from the galaxy has been so stretched and reddened that it's not visible in the blue, it's not visible in the green, it's not visible in the red. In fact, this is the reddest that Hubble can ever see, this H-band filter, which is a wavelength of 1.6 micron infrared. Once it gets to redshift 10, you might be lucky and see it in this filter. It's not going to be in anything else. And this is the limitation of Hubble. Hubble can't actually see beyond the redshift of 10 because it doesn't have any regular filters on it to work with. So the James Webb Space Telescope was partly, the simple answer is every time we think we've seen the most distant, oldest galaxy, when you move to a new filter, you see a more distant, older one. And with Hubble, we keep seeing galaxies at redshift 10. The question is that a technical limitation because does Hubble can't see them further, or is that actually the very first galaxies ever made? At the moment, we don't know that, and James Webb is designed to answer that. So as we'll see, there's two interesting things about James Webb. One is it's much bigger than Hubble. So Hubble's basically a kind of 2 meter diameter telescope, so it's still pretty big. From here to the wall. James Webb Space Telescope mirror is 6.5 meters. That diameter, okay, not bad. And of course, the collecting area of the mirror goes as the diameter squared. It's the area, okay? So it's 10 times the collecting area of Hubble. And it's designed to see red, 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 much redder off the side of this graph, so that if this galaxy keeps getting redshift, we will still be able to see. So it's an infrared telescope. In fact, the James Webb Space Telescope can't see anything in normal light. It doesn't have any normal cameras in it. It's purely an infrared machine. And actually, for that reason, they're trying to keep Hubble going for a while because it can see in the optical and complement it. Right, just as an aside, in case you're wondering, I've said that we can't see galaxies beyond redshift 10 with Hubble, and that's about 90% of the way back. Can we see anything earlier? Well, the answer is yes. You can actually see the microwave background, which is the image of the universe basically about 100,000 years after the Big Bang. These are not stars and galaxies. This is just an image made in microwave showing the gas temperature when basically the universe expanded to the point where atoms formed from the first time. This is basically all the way back to the universe, the beginning of the universe. There's less than 0.1 billion years left. And you can't see past it because it's like a fog. It's like an opaque fog bank at this time. If you cared, that's a redshift of about 1,100. So the universe was about 1,101 times smaller than it is now. At this point, these sort of things become a lot more meaningless. But that is the earliest image you can see. But it's almost like a different kind of astronomy. This was before any objects existed. No stars, no planets, no galaxies, anything, just a very smooth universe. And actually, although this is exaggerated, so you can see some hot bits and some cold bits, it's actually perfectly smooth to about 1 part in 100,000. So if this was a table, it's smoother than glass, and they've tried to exaggerate where the structures are. I mean, when this map was first made, if you remember when this happened around the turn of the century, people were pretty relieved because they had to see some structure in it, or how the hell did we get here? I mean, if the universe had been perfectly smooth this early on, no one would understand why anything existed, because there'd be nothing for gravity to get a grip of and build the first object. So let's try and put this together a little bit, and then I'll focus on the bit we're trying to understand. So this is a kind of schematic full of poorly understood things that form the universe, like quantum fluctuations and inflation. People still argue about it. Don't worry about that too much. So for a few 100,000 years, the universe was just hot plasma and gas expanded. And then this graphic's meant to show that microwave background that you can see with the microwave telescope. And then you can sit here enough and look at further and further away objects all the way back to try and see when the first stars and galaxies. And there must have been something which is nicknamed here the Dark Ages, when the heat from the Big Bang died out, but there were no stars or galaxies or anything, so it would be completely black. And what we're trying to do is basically work out where that ended and how it ended, because we want to see the first stars and galaxies. That's kind of a schematic of the same thing, we're trying to show that Hubble can see back to a certain redshift of 8 or 10, and James doesn't actually mean James Webb Space Telescope is flown back to the Big Bang. That would be ridiculous. So when you see these things, they often have, there's redshift along the top, sorry if I'm boring with redshift. So today redshift is 0, if you can read that number, goes all the way back to about 1,000 background. Here is time. It's the same thing but different axis, billions of years ago, 0 billions of years ago, to 13 billion. So the scale is really stretched out. We're interested here in this first half of the years. Now, the other interesting thing around this time is after the microwave background was emitted, the universe cooled and basically the first atoms formed. So before that, electrons and protons and things weren't connected, they're just flying around in the whole plasma. Once the temperature dropped, they could form together. The neutral hydrogen atoms basically dominated the universe. And so not only would the universe have been completely dark, it would have been made out of neutral hydrogen gas. And then there's an interesting thing that happened called reionization, where the universe was reionized, so most of the universe had electrons ripped off the protons. This is just a simulation back about 100 years after the Big Bang. The Milky Way would have been surrounded mainly by blue neutral gas, and the stars that formed in the first galaxy would have started to ionize the bubbles and make the gas transparent again. Now, if that hadn't happened, we wouldn't be able to see all the way back because the neutral hydrogen would just eat the light as it tried to get to the universe, would just be opaque. Okay. So people are interested because it's like a kind of final phase change the universe went through. It was very hot and very plasma, then it cooled and became neutral hydrogen, and then the first little stars light up and would reionize the universe. And it's kind of remarkable because as a result of this, the first stars we still think we can see. An individual photon of light, mostly, unless it gets stuck in our galaxy, travels the full 13.5 billion years without hitting anything into our telescopes. And people kind of assume this is fine, but when you think of it, it's kind of remarkable that you could cross the whole of the universe without hitting a bit of dust or a bit of gas or anything like that. So once the universe is reionized, then people think the first stars and galaxies were the things that reionized the universe. So I think I'll skip this. It's slightly too technical, but this maybe isn't. This just shows you what they notice what's going on here. So this is redshift again. There's lots of observations with absolutely massive error bars and this bit of a shambles and this theoretical model. People think that the universe was reionized sometime between redshift 9 or 10 and redshift 6. But we don't know, and we haven't found the galaxies or stars that did it yet. So, trying to connect to the research we're trying to do with the James Webb. There's 3 questions which are connected. The basic one, and the reason that the James Webb Space Telescope is sometimes called the first light machine, is that we still haven't seen the first stars and galaxies to form after the Big Bang as the universe cooled. So and this is sometimes called cosmic dawn. And so we haven't seen it yet. We don't know whether it was a dramatic event that happened very quickly or if it happened very gradually. In some models, it's a really slow thing, but some early stars form and they heat up the gas around them and stops it collapsing and slows the whole thing down again, and then it happens in successive waves. In other models, everything just switches on really quickly. Did these early stars and galaxies cause cosmic reionization, or was it black holes and quasars that did that? We don't understand that yet. And then what did the first galaxies look like and how did they form? There's a kind of technical thing that's of interest here, that when people look in our galaxy, if you've seen these pillars of creation pictures that the Hubble took, there's a kind of picture called the astronomy image of the century or something, showing these big clouds of gas that stars form out of. In our galaxy, stars form out of clouds of gas that are dominated, that cool using oxygen and carbon and nitrogen and some iron, so the things that make your body. And they're important for the gas to cool and collapse. But the first stars, uselessly called population-free stars. This is classic astronomy nonsense. Right? The Sun is called a population 1 star, earlier generations population 2, first ever stars population 3 for jargon reasons. The first stars would have to form pure out of hydrogen and helium because that's all that was left after the Big Bang. And so people don't really understand what that would be like. Some people think that would just produce very massive stars that would last a very short amount of time and might never be visible. I should say there's small enough numbers here in the audience that if I'm not making sense, just shout out, wait a minute, stop talking rubbish or you're conning me or something. So there's lots of theory about how the first stars and galaxies formed, but there's no observation yet. So coming back to the telescopes then, in that video I showed of the light being stretched, the reason that Hubble was resurfaced in 2009, this is the final resurfacing mission. You can see the astronauts. Basically, it's like taking the garage to the services field. The garage people have gone out to your car. They're taking out the old instruments and they put in the new ones. They take out a lot of old instruments from the old and put in another acronym. Sorry, Wide Field Camera 3 was the first infrared instrument to go into Hubble. And that was put in to see, well, to do lots of things, but from our point of view, to look again at the Hubble ultimate field and infrared to see what were the most distant galaxies we could see. And basically, with this, you can see this is another spectrum of the galaxy. And again, these filters, green filters, and these are infrared filters. There's a telescope Pete mentioned at the beginning called Spitzer, which is a little infrared telescope. It's 80 centimeters wide, which is capable of seeing here. And so when you're looking for one of these objects, you're looking for an object that's gone in the optical, but you can see it in these infrared filters. And if it's bright enough, you could also see it far from the head. So that's a kind of schematic. That's what you actually see. That's how unexciting this stuff actually is. Okay. So this all looks great, you know. We'll hope it's not there to see it. The data, look at that. So with Hubble, that was one of the most distant galaxies we could see. This is all the optical filters stacked together, absolutely nothing there, but it's there in the Y band at about 1 micron infrared. It's not just a glitch, it's there in the next infrared filter in J, it's there in H. And you can actually rule out anything else but a high redshift galaxy from that point of view, because there's nothing else except a high redshift galaxy with the light being redshift out the optical. It's there and then just disappears in the optical. You can see another problem here, because this is a whole galaxy and it's a blob. It covers a bit of huge. So trying to understand these other galaxies is a challenge. So we used Hubble to try and push this out beyond redshift 5 or 6. Again, this is a picture of these filters. I was in the talk that I thought was explaining this quite well, and somebody put up their hand and said, "Why are you showing us all these jellies?" These are not jellies, these are just meant to be saying this is a chunk of light again, blue, this is the green, etc. And the white curve is like the video I showed before. If a galaxy redshifted to 8, it should be visible in these filters and gone here. 10, it should be visible in these ones and gone here. And 10 is really the limit for Hubble. If a galaxy is at redshift 12, it's barely visible even in the next filter. And you probably don't really believe it, because it's not visible in any of this stuff, and maybe just get one little blob. And when we published this stuff in 2013, again, you can see the reality is horrific. These are, at the time, the 6 or 7 most distant galaxies we could see. And these are the positions in the Hubble ultimate field. Got one very ropey candidate at redshift 12, that I guess the James Webb Space Telescope will tell us if we're right or not. But basically, you're running out of Hubble's ability to see any further. This was still pretty exciting stuff at the time, and so we appeared in Horizon. And if you want to see kind of a TV documentary version of this still is visible on YouTube and comes up on BBC Two now and again. That they did partly in America and partly in Australia, and then came to Edinburgh and finished it off with stuff featuring myself and a colleague at the Observatory. So it was big news at the time, but that was as far as we could get it. And this is a very technical graph, but here's my redshift again. This is showing where we were with Hubble, and these are all the different theoretical predictions. Basically, we've got to a point here about redshift 10 where people could only maybe get 1 or 2 galaxies. And this is the density of galaxies in the universe. And by redshift 12, it's uncertain by the order of magnitude. This is a log scale. So this is Are there that many galaxies? Are there that many galaxies differing by a factor of 10 or something? Nobody knows, because Hubble's run out of steam, essentially. And this is all still fairly recent stuff, so people are kind of working away, waiting for James Webb, desperately milking all the existing data. And when we published our version in Edinburgh, this was the version from Switzerland and America, and these were our versions using the same data. So it's just complete confusion. It's what always happens when people try to push a facility to the limit. Have we seen the first galaxies? Well, certainly not, because you might think, I'm just showing you these little blobs, you might think you can't tell anything from that. Actually, from the colour of the galaxies, even in 3 bands, you can tell whether the galaxies contain nitrogen, oxygen, iron, or whether they're just pure helium and hydrogen galaxies. And that's because if they just consisted of hydrogen and helium, they would be incredibly blue, and you can ask me about that later if you want. So perhaps remarkably, although we can hardly see them, we can tell that they still contain normal chemical elements. So they already, only about 500 million years after the Big Bang, contain the elements required for life, which you could say are carbon, oxygen, nitrogen, iron. And these need to be made in stars and then recycled into successive generations of stars. In some ways, this is a surprise. You get that the universe that's 13.7 billion years old, and you're only 0.7 billion years into that, and you've already, something's already happened to make all the elements required to make you and me. So there must be still earlier generations of stars that we can't see otherwise. So we're already seeing second generation galaxies from the weekend. So we've never seen yet the very first stars in the universe which manufacture the first heavy elements, and that is the kind of holy grail of cosmology. So let's come up to this week then and look at the James Webb Space Telescope. So the Constant Christmas Day. There's a lot of Edinburgh interest here because it's got 3 instruments on it, and one of them, the mid-infrared instrument, was led from Edinburgh. Gillian Wright was the PI, not private investigator, principal investigator for the mid-infrared instrument. And it was finished quite a long time ago, waiting for the telescope. So this is 6.5 meters or so across. Again, you might have read about this, seen a lot of this. It's made out of a mirror that's beryllium. It's got to be very light and not bend much when the temperature changes. Coated in gold, very thin layer of gold, because gold is very good for infrared astronomy. It doesn't emit much in infrared. A lot of ground-based telescopes and all that to be coated in silver. Then the light comes in, hits this mirror, goes up to the secondary mirror, and goes down through the hole there, and out back to the instruments, just like standard reflecting telescope. Okay, so the basic design of the telescope is quite simple. And then these things, the sun shield, there's a lot of controversy about the sun shield. This 5-layer thing is designed because the telescope's going to work in the infrared, right? So you don't want it to be warm, otherwise it will just see itself. A bit like going out to do your optical observations at the astronomy club and suddenly wandering around with loads of flashlights. So you don't want any glow. And so the whole telescope is 40 Kelvin, so about minus 230 centigrade. But the sun shines up here, and actually the temperature of this part of the sun shield is about boiling point of water, 100 centigrade. And the reason for these series of things is it gradually drops the temperature. This next one's a bit cooler. The telescope itself here operates at about 40 Kelvin, so about 360 degrees centigrade colder than this one here. So you've got the sun shield, but of course you want to see the sun through your solar panels to get some power. So the solar panels are here. So they see the sun, then the sun shield, which kind of blows up like a camping mattress. This one of the final delays was like some kind of IKEA nightmare. They practiced the whole sun shield expansion in the lab, and somebody had forgotten to tighten the 2,000 screws. It was just their one job. And apparently the screws blew all over the Norfolk Grumman lab, and they lost half of them, and the whole thing was a complete shambles. So when you think sometimes these things are blown by high-tech solutions, this was just, I don't know, some apprentice engineer who was given a spanner and told to go around it. So anyway, it seems to have amazingly worked in situ. And so what you have is a telescope that's hiding from the sun behind its sort of telescope-sized multiple sunshade, and therefore can only look at certain places at a time away from the sun. It's kind of asking a question. You can guess that's enough, and that's it. Why is it going to revolutionise things? So I've tried to scale these pictures to the right size. The previous telescope that could really see in the infrared was Spitzer, which I've mentioned. It's less than a metre diameter. Compared with 6.5 meters, obviously there is 3 times bigger. So maybe the more relevant comparison is this to Spitzer, which was the previous telescope we could see in infrared. And compared to that, the collecting area of the is over 50 times bigger. So it's a real step change. The other interesting thing is there's no point making a telescope that's going to keep you nice and cold, etc., and putting it close to the Earth. The reason that Hubble couldn't see it far enough in the red to see distant galaxies is because it just get warmed up by the Earth. You're only 350 miles above the Earth. The Earth is glowing all the time. So to stick it out 1 million miles away, this isn't quite to scale. This is the sun. So this is actually 93 million miles. This is 1 million. There's these weird points in 3-body gravity where things are stable. So again, shout at me if I'm not too technical. Usually, as you go further out from the sun, things fall further behind due to the nature of gravity. So the outer planets go around more slowly than the inner planets. At this point, Lagrangian Point 2 is a place where the James Webb Space Telescope feels the gravity of the Earth and the sun combining in such a way that it keeps up. So it's almost like locked into the roundabout. So it won't fall behind. It will keep up with the Earth, which is good because we need to keep talking to it to get the data of the telescope to come down. And it actually sits out here, wandering around in a little orbit around some stable point. And the lifetime of the telescope is determined by little rockets having enough fuel to keep it in this semi-stable orbit. And the good news about the launch was they also thought, you know, when ESA launched this thing on the Ariane rocket, they tried to get the trajectories right. They thought they might have had to use a lot of fuel just to stop here. You know, the telescope's coming towards it, get the rocket faster, put the brakes on. And if they'd had to do that, they'd have used an awful lot of fuel that could now just be used to nurse it with the position. So it's meant to be a 5-year mission. They now think they have enough fuel for it to last 20 years. Let's see if that happens. So they have to put it out, you know, to keep it cold. It's too far away for any astronauts to fix it, and it has to hide behind the sunshade to keep it cold out there. This is a simulated image. This is a real Spitzer image of the sky, that little infrared telescope. And here's a kind of simulation about what the same part will look like with JWST. So that's partly just the resolution and it's partly the extra depth. So you go from just useless blobs that you can't tell anything about them to actually seeing real galaxies in the image. But it turns out, as I said, that actually it's better than that. And so you may have seen these images released online about 3 weeks ago, just comparing what the Spitzer Space Telescope could do at a wavelength of 8 microns in infrared. And this is a real image of this time of the same patch of sky using the media instrument, which was built at the end. And so, you know, is that a galaxy? Is that a star? It's a star. You can tell it's a star from the diffraction spikes. Why are there 6 spikes? Because the mirror is made up of little pixels. So you get these distinctive patterns from individual stars, as you always do. You can see real galaxies, you can see gas and dust going in from red. So this is the sort of technical leap that we're talking about. This is just nearby stars in our galaxy. This isn't a particularly deep image or anything. So it turns out its image quality is better than expected or predicted, which doesn't happen much in science, certainly not in astronomy. So I'll finish with a little bit of just technical details of the instruments for some of you interested in just explaining what we're going to try and do with them. So this is what's called the focal plane of the telescope. So the light comes into the telescope of the big mirror, of the secondary mirror, through the hole in the main mirror, then down to the instruments. It lands on this set of instruments. And so this is the main near-infrared camera called NIRCam. It's got 2 arrays of 4 infrared detectors. And then this MIRI over here, I won't bother with the other instruments, but it sees a longer wavelength well into infrared, but it sees a different bit of sky from the bit of sky that this is. Because the light's falling down into this substance. See these 2 patches and maybe see the other patch. And a lot of what we're trying to do in our program is get MIRI imagery from the same bit of sky that's already been imaged with this near infrared. And so this is how you do it. You design a program where you walk across the sky, taking images in the near infrared camera and dragging the telescope in such a way that this camera is then dragged across the same bits of sky that this camera sees. But you can't do that if you're just making one pointing. So what we did was we designed a program where you do a lot of pointings, and that's why it takes a lot of time. And you just set the way gradually across, and at least the central region will be covered by both instruments. This gives you coverage all the way from 1 microns to 20 microns. In principle, if there's galaxies at redshift 30, you should still be able to see it if you want. And so, remember at the beginning I mentioned these tiny 2 fields called the Cosmos field and the UDS field. So they're going to be using MIRI and NIRCam, these 2 instruments. And you might say, why did we choose these fields? Well, they've already been looked at with the Hubble Space Telescope and the OPT. In that candles program Pete mentioned at the beginning. So you go where you already think you know everything, and you go with a new instrument, see if you can find out some more. So this won't be in this survey, won't have any data taken yet. We'll get data at the beginning of August, and then data again in November, and then we'll get data again in January, and then again next July. So it's going to be spaced out 4 times over the coming year. And the reason for that is you step one way and then you want 6 months later to come back and step across the other way to complete the survey. So we'll get the first data from this, a few test images in August, and then it will work its way through the coming year. But a week on Tuesday, the instrument commissioning teams have been taking data that they're going to release to the public. So on the 12th of July, which is Orange Walk Day, but I don't think that's got anything to do with why they've decided to release it. I think that's something set to NASA. On the 12th of July, they will release public images, and then on the 14th of July, 2 days later, they're going to release all the raw data for scientists to check their data reduction pipelines and things like that. Nobody knows what's quite going to happen. The Space Telescope Science Institute in Baltimore is running this, the same people that ran the Hubble Space Telescope. And nobody thinks their websites have been subjected to what will happen on the 14th of July, whenever the world can access, in principle, all this many terabytes of data. So it's been kept quite secret. We know that they've done some test images, but they say they're going to release 3 images that kind of show the full capability of the telescope, including 1 deep image, not big images with lots of pointers like this, but maybe just a couple of really deep pointings to show how far you can see. So that's the week after next, so that would be interesting. Yeah, this is just to show what we'll be able to do. So with James Webb Space Telescope, if you cast your mind back, this filter here is basically as far as you can see with Hubble. With Webb, these are the red filters, it's golden and red. And so we get data in all these different filters of the black dots, and then you can fit the galaxy spectrum to work in. We've got Redshift 7, not just 2 blobs, but all the different data. Redshift 8, you can even maybe detect if there's emission lines from oxygen in the spectrum. Redshift 10, which Hubble couldn't really do, there were 1, 2, 3, 4, 5, 6 data points. You actually will be able to tell at Redshift 10 whether it's a young blue galaxy or an older red galaxy that's formed in 15. So we'll actually be able to age date galaxies at Redshift 10, whereas at the moment we can hardly see them at all. So this is the kind of excitement, and although it sounds I think this argument about whether galaxies formed early or late, if we were right in Edinburgh, we expect to see about 37 galaxies at Richard Hole. These other people were right, maybe 6 and 2 and 12. So this is just a quantitative simulation that we'll be able to tell if the first galaxies formed maybe at Richard 20 or more like Richard 12. And this is just, these are simulations of the colours of galaxies, about how you can tell if they contain nitrogen or carbon or not. Very blue slopes will tell us that we've seen the very first galaxies made out of hydrogen. I sort of said this before, so this primer survey is say 4 times during the year, so we actually hope to start small writing, I apologise. There's a window, see the thing about the James Webb Space Telescope. There's a box around. Glasses. Very bad simulation. James Webb Space Telescope sun shield. Okay, so if the projector's the sun, the space telescope can only look that way or that way because it's kind of tied in behind the sun shield. And so if you want to see something 6 months later, you go that way. So the result of that is you get these windows where we can see these same part of sky, just because the telescope always has to hide behind the sun shield. And so we're hoping the schedulers will make sure that we get, well, we missed May 22 because it was meant to be ones that so we'll start here, July, August 22, and then get more data in November, December, January. This will just get flipped around to June 2023, towards the end of the first year. So, yeah, we find ourselves now less than 2 weeks away from the first data. We know from the rumours that everything works. I had a YouTube video here showing it unfolding, but maybe since it's unfolded, it doesn't really matter very much. If I'm online, I could play that to finish. Let's see what happens. I show this because this is what had to happen in the 6 months since launch to now, because the telescope was bundled up inside the Ariane rocket. And the surprising thing is all this happened. So it did quite a lot in the early days. So after Christmas Day, they were continually checking, this is unfolded, this is unfolded. See, even though it was too big to do it with telescopes, so they knew the sun shield had worked and that the screws had been properly tightened this time within a week. It's kind of easy to take for granted that that would just happen, but that's some piece of engineering to make all that happen. And then you might say, what's it been doing for the last month? For the last 5 months, basically cooling. It takes several months to cool down to this 40 Kelvin inside this, because they're not cooling it, it's just passively cooling due to the coldness of space and being shielded from the sun. Which is a technique that this idea that you could passively cool a telescope was, I just stop this, hang on. Was also invented by somebody at Edinburgh. I don't know if any of you knew, a guy called Tim Harlan was the first person to come up with that. You could put a telescope in space. You didn't need to cool it down, just if you kept it shielded from the sun, it would gradually cool itself down because space itself is so cold. So I'll leave it there then. Sorry if I've overrun. Happy to field any questions.
Just a few.
How much data was it collected now?
Well, one of the problems is that the data download system is now 10 years out of date. So the main limitation of what the telescope can do is how much data it can store in its disks sent back. It'll be nearly it'll be in the gigabyte, not the terabyte. Yeah, so it's the problem is that like any rocket, if it being so delayed, the technology on board this is 15-year-old technology. And so that, yeah, one of the problems is that downloading the data. Knowingly a limitation now. It's a bit like your computer, you know, what used to be great disk space is now rubbish, and you just put it in a pen drive. It's probably less storage in James Webb than a pen drive.
But the trouble is, it's now got to last 4 times.
Yeah, but maybe that's a good thing, because then there's no panic to just get through all the data it can produce in the first 2 or 3 years.
The galaxies that we're seeing, which are relatively close to us, with this new telescope, we're going to be seeing galaxies that are much further away. What's your thoughts on what you're going to take up off of these galaxies that are they going to be in a state of meltdown, or like history and geography, or the one's going to be warming up, or the one's going to be?
We already know that the ones we can see with Hubble are much smaller than present-day galaxies. Nowadays they'd be called the dwarf galaxies. So that over the next 13 billion years after you see them to now, they'll merge with other galaxies and form into much bigger structures. And there's nothing as big as the Milky Way in these early galaxies. They're much smaller.
So they're one of the bigger galaxies.
We're one of the bigger galaxies, but that's because over the, you see your first galaxy, you're really just seeing what would be the core of the end galaxy. It will gather more gas around it, more stars will form, other galaxies will merge with it, if you believe the simulations, and will gradually build up. But one thing I should say, if you've got a different speaker, they would tell you that a completely different thing of interest in this telescope, which is to look at some of the closest stars for planets around them. Right, and again, you need infrared because the planets are outshone by the stars in the optical. But if you look in the infrared, you can see the glowing planet. So, ironically, probably the big flagship projects are first galaxies and can we look for life in some planets around nearby stars. One's away at that end of the universe, and one is, relatively speaking, right here.
So the thoughts is, and the further away ones that we're looking, obviously. He said you got another speaker who's looking for planet type lifespan. So, what's your thoughts on the further away galaxies?
Well, the thoughts are we've not seen the first galaxies yet. That's what I'm saying. It's up until now it's been a technological limitation. I mean, this sounds a weird thing to say. The Holy Grail would be take a deep image where you didn't see any more galaxies. Because then you know you'd see beyond the first galaxy. You're looking for a gap almost. You're trying to say, right, the technology's allowed us to see back to here, and the galaxies stopped here. Then you would have found the very first generation.
When you look at all this technology and knowledge and like that, there's only one planet out there.
What?
Like this one.
Well, I mean, in some ways we now say that our Milky Way, so we know that if we count the stars in the Milky Way, so it's 100 billion. All the planet surveys so far suggest that our solar system is fairly typical, so let's call it 10 planets per star. So that gives you one with 12 zeros planets in our galaxy, and there's another 100 billion galaxies. But nobody knows how unique our planet is. It's probably not unique in terms of there'll be rocky planets at this kind of temperature, but the question is how. Some people would say that, you know, we're so average that there must be life everywhere. And some people would say we're so unusual that the universe needs to be this big to have life once. There's probably a middle road where most people think there'll be primitive life, you know, it's not so far from chemistry in lots of places. Given the dinosaurs ran around for 100 million years and didn't come up with the James Webb Space Telescope, it's it may be sort of very, very rare event to get technologically proficient life, and it may also be, as we well know right now, that technologically proficient life doesn't last very long. I'm afraid.
Yes, the Hubble Space Telescope has done a marvelous job to start any problems, but what is its future? Has it got one?
Sorry, some of that distraction. YouTube history. Sorry, what were you saying? Which telescope? The Hubble.
The Hubble.
So-
what's the Hubble?
The Hubble, there's a small gang of people running the Hubble now. It can't get any more instruments because, of course, the shuttle blew up and was decommissioned, so they can't go and do anything to it now. It points with a set of gyros. It's got 3 gyros, and every now and again one of them breaks, and they manage to fix it with some electronic jiggery pokery remotely. And they're now running it, they know they can run it in 2 gyros now. When it stops being pointable and usable, they'll then have a challenge of trying to get it down without killing people. Okay, as you always have with a big satellite and decommission it. So then the challenge will be to land in the Pacific and not in Elgin. It will have to be brought down, but they can't. It doesn't have the rocket power to fire it away. But because it's quite possible, there's a lot of people going to, want to use Hubble again. This sounds a bit strange, but you might find some objects with James Webb Space Telescope you're not expecting. You might want to follow them up with Hubble. Maybe not the very high redshift where I've said that they're invisible to Hubble, but if you found some interesting objects in nearby galaxies that were unusual and you disturbed them with James Webb, you might apply for Hubble time to follow them up in the optical to kind of complete the picture of it. It's quite difficult now to kind of come up with breakthrough Nobel Prize winning science in Hubble, given it's been around for 30 years, but that doesn't mean it's not a kind of useful workhorse. And although it's expensive, it's not expensive now. It's just flying for free with about 3 engineers scheduling it and running it. So the common wisdom at the moment is to keep it going until it dies. Now, it's partly because NASA and ESA have not got their act together to build another optical telescope. There's not a kind of optical successor. There's been so much excitement about getting big and moving to the infrared with the James Webb that people haven't. There's talk now about building a future optical telescope that's bigger, but there's nothing around that can do what Hubble can do in the optical at the moment. So keep it going.
Undoubtedly, Hubble has been really important in engaging the general population with its fantastic images in the later days. So I would have thought having something to follow on from that would be a benefit that it brings citizens.
Yeah, I mean, there's probably an important but sensible development in the Space Telescope Science Institute in Baltimore, which did such a good job of all the outreach and publicity and image production and posters and videos for Hubble. They're the same people who are going to be involved in James Webb. Basically, they won the contract to also run the James Webb Space Telescope. There was competition. The people that ran Spitzer over in California wanted to run it, but the Space Telescope Science Institute won the contract. So there's no reason to think that what was done in terms of publicity and image production and public things you can use in your public talks with Hubble won't be delivered by the same gang of people who need a job, and I'm probably glad that James Webb has come along to give them new images to work with.
Anyone else?
Recently, the sun shield has been hit by a little particle.
Well, it's worse than that. The mirror was hit by a particle. And one of these hexagonal things is already a dent. It was hit by a meteorite going at about 10,000 miles an hour last week or 2 weeks ago. It was on the news. So it's sort of okay. I mean, optics is such, you can have the odd little defect in a mirror and you won't notice. If a big meteor comes along, it'll annihilate. I mean, that's just life in space. I mean, if you remember the movie Gravity, get too much junk flying around and you're going to die. I mean, there's a reason it went to L2. There's these other points they could have put it, which are stable points where lots of debris just falls in. L2 is a kind of unstable point where space junk like meteors and rocks and things won't gather, but there's no way to be sure it won't be hit by the odd thing. And this was a thing about the size of a grain of dust. A grain of dust going at 10,000 miles an hour. You know, they used to say the people building the Forth Bridge, if they were hit by a wheel from the top of the Forth Bridge, just killed them because it was going so quick. So this is like an exaggerated version of that. So it's not been hit by something very big. It didn't break anything. But yeah, it's maybe a slight worry that in the first few weeks of operation, it's already been hit once. Nothing we can do about it, really.
If there's any more questions, I'm sure we can encourage you in the tea break. But just before we go, give me a little bit for you.
So thank you for a really fascinating talk. For our first talk back, it was a really good talk to have. So what we've got is we've got some whiskey glasses in here, etched with Sigma's logo as well. And the idea is you can come back and give us more talks, get more glasses, and build a set, like just like you used to do in the olden days.
As I was driving through the downpour, I kept seeing distillery. I thought, maybe I should have stopped.
Well, maybe we did last week distillery. But thank you very much.
Okay, so teas and coffees will be up. Let's Glenn is getting ready. We'll be back in the second half. We'll be back by about 5 past. Get your coffees when you're ready. Come back in. We'll try and get going again about 10 past the latest. We should be finished by half an hour. I would hope. Tim, that'd be good enough for you. Yeah. Okay. See you. Right, I think I'll kick off. So it's about this. Okay, we'll kick off the second half. Say this half, just be sure your August Stewart is here. Sorry, Stuart. Yeah. His space music is brilliant. So we're going to kick off now. Tim's going to do an after basics for us, and I think it's going to cover a little bit of rocks. Jim was on the moment and then cover distances. So over to you. Okay, thanks very much. It looks a bit squashed, but I think it's okay. Right, well, first of all, fantastic talk. Thanks for that. Bringing us up to speed on James Webb Space Telescope. There's some of the things that Ian was talking about are what I'm going to be talking about. So a bit of overlap there, but perhaps give some of you, if you're not too sure about things like parsecs and light years, give you a little bit of a further explanation of those. So, am I pressing the right one? Oh, okay, I have to use the keys.
Or just the next slide.
You'll get all VTC.
Okay.
So this is one of my astrophysics. So those of you who have been to these meetings before will be familiar with the idea that it's taking a small topic and talking about it for a little while, a few minutes. So today's oh, is it working?
Give it a dongle. I have one.
Right. Okay. So today we're looking at
units of distance. As they said in the Hitchhiker's Guide to the Galaxy, space is big, very big, and that means any distances that we're going to be referring to, if we use regular day-to-day units like miles and kilometers, you end up with really, really big numbers, which become not only difficult to handle, but also to comprehend. So what we're going to be looking at this evening are three units. First of all, the astronomical unit. I'll put in brackets the standard abbreviation you see in astronomy and astrophysics books about that. The light year, which is LY, and the parsec, PC. So first of all, the astronomical unit. So the astronomical unit is pretty much, if you like, the average distance between the Earth and the Sun. And it's a unit that is used for referring to distances within our solar system, and perhaps more recently in other solar systems, like Ian was referring to, exoplanet systems. And what you see up there is a definition of an astronomical unit in kilometers. So for those who use older units, it's about 93 million miles. But the astronomical unit, which has quite a history of measurement, going back quite a long way. Historically, astronomers put a lot of effort into working out that figure there. So that's pretty much the unit adopted by the International Astronomical Union, who determine what these units are. So when we look at our solar system, you can see in the middle column there the distances measured in standard day-to-day kilometers, and you can see how representing them as astronomical units makes referring to the distances so much easier. And you can see the Earth is one there, and then Mercury and Venus will be less than one because they're closer to the Sun than the Earth, and then going outside of the Earth's orbit, they gradually get bigger and bigger and bigger. So that's the astronomical unit. Light year, which Ian was referring to, is the distance that's travelled by light in 1 year. Now, 1 year we're referring to there as 365.25 days, and light travels at that speed. We're referring to it travelling in a vacuum, because essentially that space is a vacuum. So if you do the mathematics on that, it turns out that 1 light year is equal to nearly 9.5 million kilometers, or a trillion, 9.5 trillion. So in miles, that's nearly 6 trillion miles, and in astronomical units, 63,000 or so astronomical units. So it's quite a long distance, and that's the distance travelled by light in 1 year. So M31, the Andromeda Galaxy, is almost 2.5 million light years away, and that means that the light has taken that amount of time to reach us. Now, this diagram shows, I think it's actually quite an interesting diagram. It shows pretty much to scale the size of our Milky Way galaxy, which is about 100,000 light years from side to side, edge to edge, and the Andromeda Galaxy, which is about 140,000 light years. And in this scale diagram, it is a scale diagram, I checked with a ruler. Well, actually, when you look at that, it makes you think, well, actually, the Andromeda Galaxy is quite close, isn't it? And that's a very important thing, because it is, and it's getting closer. The galaxy is moving towards our galaxy. That's a talk for another time. So there we've got light years, and then, as Ian mentioned, parsecs. Now, parsecs, the term parsec comes from parallax of 1 arc second. Now, parallax is a measurement which is very important in astronomy. If you imagine you've got the sun and the earth and somebody looking at our solar system from afar, parallax is the angular separation between the sun and the earth as seen from this point. Now, 1 arc second is a measure of it's an angular measurement based on a circle having 360 degrees, one full circle is 360 degrees, and each degree in a circle, in that circle, can be divided into 60 arc minutes, 60, or sometimes called minutes of arc, but arc minutes is easier. And each of those minutes, arc minutes, can be further divided into 60 arc seconds. So in a full circle, you've got 360 degrees. Each of those degrees has 60 minutes. And each of those minutes has 60 seconds. So if you do the mathematics on that, you'll find that that's actually a very small angle. In fact, a second of arc is so small that if you were at the center of the Earth now, and you were looking at us up here through the solid Earth, and one of us walked 30 meters, which is what, 12, maybe 3 times the width of this room, seen from the center of the Earth, that distance would be 1 second of arc, so it's minuscule. Okay. So what we do in terms of distance is we say that if you are 1 parsec away from the Sun-Earth system, then this angle is 1 second of arc. And that works out to give you 206,000 astronomical units as the length of a parsec, or 3.262 light years. So it's actually a long way, 1 parsec, but it's actually 1 parsec is less than the distance to the nearest star. So the nearest star is about 4.3 light years. So that's 1.5 parsecs. But the advantage of this is that once again, it's reducing the size of the numbers that you have to handle when you're talking about distances. So what I put up here is just a brief table taking some well-known objects which we all know about in sigma and showing the distances written in parsecs and light years. So Sirius is 2.6 parsecs away, or 8.6 light years, and increasing. And you can see M31, the Andromeda Galaxy, which Ian told us earlier was about 2.5 million light years away, is, well, about certainly less than 1 million parsecs. Now, I don't know about you, but for these, particularly the stars, I prefer seeing the distances in light years. And I was listening very carefully when Ian was talking, and it is so much easier to refer to light years because it gives you a sense of time. Whereas a parsec is just a little bit more clinical. So to know that Sirius is 8.6 light years away, to me, I don't know about you, it seems much more useful. It's taking light 8.6 years to get to us from that star. Whereas to say it's 2.6 parsecs away, doesn't sound so great. So my preference when you're talking about stars and galaxies is to actually, if you can, stick to light years. But when it comes to doing astronomical calculations, I'm sure Ian will agree.
Yeah, I can comment. I mean, the good thing is a light year is about 3 times a parsec. You don't need to remember both. You just say which
Exactly.
I think sometimes people don't like to use light years because they worry that people, because it's got the word year, and they've forgotten it's distance.
Yeah.
They think it's time. So as long as people can read into their head that a light year is the distance, then it is an easier thing to envisage.
Yeah. And as you go further and further out into the universe, So the number of parsecs of distant galaxies becomes huge. So you see abbreviations for megaparsecs, million parsecs, and gigaparsecs, which is 1,000 million parsecs, NPC and GPC. Which brings me finally on to this, which I'll be interested to see what Ian has to say about this. This was announced in April or thereabouts. Supposedly the most distant observable galaxy, HT1, and I put a question mark there because there is a question as to whether it is a galaxy or not. And I think, am I right in saying they will need to do some spectroscopy on that?
Yeah, well, there's a bunch of things, but
Yeah.
actually 10 to 12 arrivals for the most distant known galaxy. James Webb Space Telescope will certainly
Something like that problem. Yeah. If it is, I think the estimate was, in terms of parsecs, was about 10 gigaparsecs, as far as I can see, which is quite a long way away. But yeah, I'd be interested to see what the James Webb Space Telescope has to say about that. So that is astronomical units, light years, and parsecs.
Clear now. Next one. Okay, just finish off with a quick news. Right, so this I mentioned in the first half about the sort of future of the meetings, the way we should do this. As I say, we're going to try and do as many sessions like this as we can, but there is a call for people who still want to do a bit of Zoom, which we're going to do them in the winter months, January, February, and March. Because in the past, since I remember Sigma, we've always had trouble in one of them months of getting a speaker out, or even getting youth coming out, so there's the growth in the. What that does actually mean is that we can get speakers from all over the world. In fact, the November meeting this year is going to be on Zoom. It is Neil Reed from NASA.
Yeah, he's a Space Telescope scientist.
Space Telescope scientist. He'll be joining us from America. Whether we do it here in the hall, not decided yet. Whether we Zoom in here or whether we'll talk about that and go from there. But we will start doing, say, these more astro meetings. Bill Letty started this 7 years back. In case clear skies, keep an eye on your emails in a clear sky. We're meeting here tonight. We move around the morning a little bit. So not everyone's got to travel all the time. We might go Tower Hill. Cooper Park is, sort of solar observing, or we can go Grafton Way. We can just move around. So it's a bit fair on everybody. We will obviously still try and do our Friday night and Saturday night observing sessions. As you know yourself, the weather has not been very keen to us, just lately. But those do take a little bit more organising. These drop of a hat, let's go for it. Just go for a couple of hours, does actually work very, very well. So I say, keep an eye on emails, Facebook as well. No people are saying that WhatsApp. You'll match the back there smiling at. That brings me on to the next section, which is social media. It was in the news there, but social media, as I say, is a necessary evil, I think, nowadays. As I say, we're going to be no exception to this. What I'm looking for is a couple of volunteers who might know a little bit about social media, who could just keep it up to date. We've got a WhatsApp, we're going to meet, send that out. Yeah.
What now? Who are you not going to go to?
See the tumbleweed. But if there is anyone out there who wants to do this, let me know, and we'll also do it. At the moment, we'll just carry on doing it via email. Meeting here, email. It's not as good because you've got to check your email, but it's not so bad nowadays. You can get it on your phone. See how it goes. Let's say you don't want to be on the committee to do that, by the way. Okay. Next week we'll start that again. So if you've got any clubs, societies, schools, or anything on that talk, astronomy talk, basically talk about astronomy, let us know, and we'll get out and meet these people and spread the word. The TT coffees. Richard and Dennis do an awful lot with TT coffees. Thank you very much for that tonight, and be nice. They can always do with a hand, so for free. Just anything to give them out. So then, because they do actually need a speaker, take the speaker from me as well, previous to coming here and doing this. So Looking for a couple of volunteers there as well, just to chip in there and again, give them a break.
Yeah, we're trying to run it at the start of the meeting.
And at the end, yeah.
the talk as
Sorry. Yeah, observing nights will resume the end of next month. We normally try and start the first week share. I'm not sure what the moon's doing there. I haven't got that far ahead yet. With the weather, I don't really look more than 24 hours ahead. And if you're bored tonight, don't forget to tell your friends, bring them along, invite them along. So your first meeting is always free. Say first meeting is always free. We all know somebody's got an interest to try and grab them and bring them along. I think, you know, not friends. I'm trying to be curious. If you've got anything for me, I'll get in contact with via email or just run me in a minute. With that, I think I'll thank Jim for his wonderful talk. And I've already had people saying, can we get you back? So, Chris, put it on the list. Chris is still there. For those of you who didn't know, we're actually sending this through Zoom. We know file. Chris is on the other end, just wanting to see how it comes out. Okay, so if you've been saying anything nice about Chris, it's very cool. So Madison, Rick's there for meet the speaker and do copies. Tim, I'm joining us up short notice and was a bit of panic on myself last night. Because sounds coming along as a point sigma, and we'll see you next month with Christine R. and Dunlop. I can't say that from St. Andrews. With synchronized swimming. Yeah, I'll let you read that on the internet. Yeah, I've got Frankie Howard on the so say, thank you all very much for coming along, and we'll see you next time. Go on, yeah.
We're providing the newsletter. Tim, Helen, and myself.
We're coming up here so you get on.
Yeah, okay. Yeah, we're revising the newsletter, so take responsibility off Peter. And we're also changing its format. We're going to use something like now, something called Sent in Blue. And so it'll be an electronic newsletter. Now, what it will have is a couple of introductory paragraphs on different articles. And then there'll be a read more section where if you want to read more about it, you can just click the link and it will take you to a page on the website. There's more information on it. But what we really need with the newsletter is people to write some articles. So if you've got any astronomical related thing that you've got any knowledge of, if you could just write us a couple of hundred words about it, that would be fine. Maybe some photographs. As I say, the new newsletter format will be used from September. We're assembling articles at the moment, but if you guys could add something, that would be great. Email it to Helen or myself. We'll add it to the meeting. So thank you.
Yeah, cheers, Rich. I did mean to sort of say that. Okay, thank you very much. We'll see you next month.